I'll be going into implementation details of the inverse dynamics and the forward dynamics model. The way they are modeled is through a vector quantized variational autoencoder. The VQVA allows us to produce discrete latent codes that are sampled from a continuous latent action space. This is the only way using a VQVA is the only way we can do that. The VQVA also helps us get a more interpretable latent action space, which highly increases the efficiency of the second part of our method, where we do not need a big label data set. Um, it also the VQVA also is able to escape mode collapse, and it is also able to produce state invariant action representations, although that is not completely explained in the paper. Next, going on to how the VQVA works. The VQVA has an encoder, a decoder, and a code book. The encoder takes in the observation as an input. It is supposed to output a encoding ZT. Next, the VQVA looks at ZT. It finds the encoding inside its codebook, which is closest to ZT. That is done by optimizing this argument function. Um, Next, now that we have this encoding, we pass it to the decoder, and the decoder is supposed to produce the the input that the encoder got through and this is trained through a reconstruction loss. Additionally, the decoder input generally has some additional noise added to the encoding, um, which also helps with getting a better latent action space, a more continuous and a more clustered latent action space, where representations close together generally represent the same true action. Now, going into the loss functions that enable the VQVA to do all this, the VQVA has three losses: the main reconstruction loss, which is just the L2 loss between the input and the final output, and a codebook loss and a commitment loss, which kind of go hand in hand. So now let's say we got ZT, and the VQVA picked the encoding E from its codebook, which is closest to ZT. Now, the codebook loss first stopgrades the ZT and it pushes E closer to ZT. Um, and the commitment loss stopgrades E and pushes ZT closer to E. This makes it so that the action representations of similar actions or the latent actions are which represent the same two actions are connected to the same encoding in the codebook, allowing for easier mapping between the latent actions and the true actions in the second state, in the second part of the method. Next, so now I will talk about the second part of our method, which is the mapping strategy from the latent actions to the true actions. The authors talk about two ways of doing this. One is offline decoding, which is a supervised learning method. So here we just learn a action encoder, which um, which takes in ZT as an input from the inverse dynamics model, and it gives out A hat, which is supposed to be equivalent to AT, which is a part of the data set. Um, the how this is done is also shown in this diagram. We have a data set of observations and action sequences. The IDM takes in the two observations, the current observation and the next observation. The IDM gives out the latent action representation of the current action. And the action decoder is supposed to take the latent action or latent representation of the current action and output something that should be close to the actual true action. This is trained using by maximizing log probability or minimizing the negative of log probability. The loss function is shown here. The second mapping strategy is online fine tuning, where we use the IDM as an encoder or as a first layer of a policy of a PPO model. So here, what happens is instead of the policy getting observations as an input, it gets ZT as an input, and it is supposed to then learn a policy with the IDM as a first part of its um, first layer of its method. Um, Now, next I'll go into results, and we'll see how the online fine tuning um, method of the mapping strategy is very good in the way that it is able to outperform even expert strategies. Um, the key achievements of this paper, it is able to reach 84% of expert performance with just 200 label samples in the offline decoding mapping mode, while also using online decoding. After we have used the pre-training of LAPO, if we use the IDM as encoding, we see that its sample efficiency is tenfold when compared to just using basic PPO, where it is able to reach expert level policy with expert level strategy with just 4 million steps compared to around 40 million for just standard PPO. Um, Here we also see that our method, which is highlighted with the green light, is able to outperform the expert strategy, which is highlighted by the dotted line on the top for each map, in 9 out of 16 ProgGen games. And ProgGen is the environment that we use, that the authors use to show the working of LAPO. Next, I'll go into latent space visualization, which also shows how effective the VQVA is to get understandable and explainable latent representation for the actions. Here, this is this latent space visualization on the left is for a very simple um, game where the only actions possible are up, down, left, and right. And it is very obvious that um, the VQVA does a very good job at clustering the representations for each separate actions. And this can be used very easily to learn a mapping from the latent space to two actions with a supervised learning method or our online RL method. Um, this also makes the actions very interpretable. On the right, we can also see that this happens for almost all of the environments that we try, except for that the authors try, except for some of the environments such as Cave Flyer and Heist, where some of the latent representations from different actions also get mixed and they are not clustered completely well. But even then, our results for the author's results for those environments are also fairly decent, while and they still outperform basic PPO, showing that using the author's pre-training method is not does not lead to significant disadvantages, even in environments where it is not necessarily working optimally. Next, going into comparing LAPO with other baselines such as FICC and just basic PPO. FICC is the only feasible baseline that should be compared with LAPO since every other method here uses action labels, while the main point of LAPO is the ability to harness um, data sets where we do not have action labels. Um, it is very obvious that LAPO surpasses all its baselines by a significant margin, um, while avoiding mode collapse in every scenario and handling multimodal distributions as well. Um, by handling multimodal distributions, what I mean is, let's say for the Minecraft example, we had data from, let's say, a grassy plain and data from a cave. Since our method is not trying to learn relations between observations, and and it is not trying to output an observation directly. It is trying to learn the action representation. The action representation that is learned, it is supposed to correspond to an action, left, right, up, down, something like that. And that is not technically related to the grassy plain or the cave or the type of environment we are in. So we can still use data set. We can still use a lot of data from the grassy plain and a lot of data from the cave and still learn meaningful information from all such multimodal data distributions while also having our method work with in all such environments. Um, Here again, we show how LAPO is a superior method to compare when compared to all its baselines. And the key differentiators of LAPO compared to other baselines is it has a continuous latency space that is enabled because we used vector quantization, our joint training of IDM and FDM, and the flexibility that we get in the second part of our method, where we can use the offline supervised learning method and the online RL method to learn mappings between the latent actions and the two actions. Then next, going into the limitations and future works. In scenarios or environments where our current action should not just depend on the current observation, but it should depend on the previous n observations, where our problem is technically not an MDP if we are just considering observations as states. In those cases, our method as it is currently would not work. In which case, we would have to use something like a transformer architecture, which would help alleviate the problem. I will talk about that in the next slide as well. Um, Another limitation is even though the VQVA tries to get a state independent decoding by disentangling the information from the state, the action information from the state, the authors cannot ensure that that is actually what is happening. Um, I also talk about that in the next slide. Some other future directions that the authors also talk about is the applicability of the method on real world robotics and also the ability to harness web scale video pre-training for RL tasks. So if you were able to use the vast amount of data that there is on YouTube and other streaming channels such as Twitter, or such as um, it would help a lot with the sample efficiency of RL tasks, which is the main problem that RL researchers face currently. So next, going on to a few key points of the method and a few thoughts. Um, to solve the delayed action effects limitation, um, just expanding the method such that the IDM and the FDM can be conditioned on not just the current observation but the previous n observations would would actually just solve the delayed action effect problem. Additionally, we could also encode the previous n observations using an encoder or an encoder based on a transformer architecture. The next key point is the size of the bottleneck. So the size of the bottleneck has to be chosen specifically for every task, such that the bottleneck isn't big enough, such that the observation that is passing from the IDM, all the information of the observation cannot be passed into ZT. Because in that case, there is a possibility that the information from OT plus one would just pass into IDM, and the IDM would just disregard the information of OT. And uh, the information flow would just go something like this. The information would go from OT plus one to IDM to FDM to the output, in which case the ZT that we are getting is not a representation of the action, but a representation of the next observation. Another thing would be if our bottleneck is too small, it might not be rich enough or strong enough to represent the actual actions of the environment. So a ground has to be chosen. Next, the core contributions of of the paper. I will just go over it once more. The paper tries to come up with a method to harness unlabeled data that is generally more readily available, um, allowing us to get a much more sample efficient RL method with respect to labeled sequences. And this the paper also um, gives the potential to enable web scale RL pre-training, which would be amazing for the RL researchers, I guess. Um, that is my key takeaways from the paper. Thank you. That is it.